14 seconds. That is how long you would remain conscious in the vacuum of space before your brain simply runs out of what it needs to keep the lights on. Not an explosion, not freezing, just off, like a phone that lost its signal. Tonight, I want to walk you through every layer of protection standing between you and that 14-second countdown right now, the ones you cannot see, cannot feel, and have never had to thank. And then I want to show you what happens to real people when those layers fail. If you are new here, subscribe and stay with us. By the end of this, the sky above you will look like the thinnest, most important thing you have ever seen. Part 1. The lie we were told about space. In December 1966, a man watched his own saliva start to boil on his tongue, not metaphorically, not as a figure of speech. Jim LeBlanc, a NASA test subject working at the Manned Spacecraft Center in Houston, was inside a vacuum chamber, a room designed to strip away the atmosphere and simulate the conditions of space when his suit accidentally depressurized. And what he described afterward was not pain, not panic, not the dramatic cinematic death you've probably imagined 100 times. What he described was a strange, almost peaceful sensation. The moisture on his tongue began to bubble. He felt it fizzing, cooling, evaporating off the surface of his own body. And then, 14 seconds later, he lost consciousness. 14 seconds. Think about that number, 14. That's roughly the time it takes you to read this opening paragraph. It's the time it takes to pour a cup of coffee, to tie one shoe, to unlock your phone. It is not a dramatic span of time in any ordinary sense, but in a vacuum, 14 seconds is the complete window of useful human consciousness. After that, your brain runs out of oxygenated blood and you go down. Not with a scream, not with an explosion. Quietly, predictably, completely. Jim LeBlanc survived because a technician repressurized the chamber in time. The people watching through the observation window saw him collapse, and they acted fast. He was lucky in the most specific, unrepeatable way. Lucky that there were people at the controls. Lucky that those people responded immediately. Lucky that the machinery worked. Take away any one of those variables, and the story ends differently. Take away all of them, and you have the story of Soyuz 11, which we'll get to, because that story ends with 3 cosmonauts landing perfectly, in perfect silence, dead in their seats. But before we get there, we need to talk about the lie. Not a deliberate lie, exactly. More of a comfortable fiction that science fiction built over decades, and that most of us absorbed without questioning. The lie goes something like this. Space is a dangerous place. Space is cold. Space is full of radiation. Space is empty and dark and hostile. And the thing that makes it dangerous is all the things it has the radiation blasting through it, the temperature, the cosmic debris spinning through the void. We imagine space as an active killer, an environment that does things to you, an enemy with weapons. That framing is almost exactly backwards. Space is not dangerous because of what it does to you. Space is dangerous because of what it stops doing for you. The threat is not the presence of something harmful, it is the absence of something essential. And that distinction matters enormously, because it means that surviving space is not about protecting yourself from an external attack. It is about recreating, with perfect fidelity and perfect reliability, the precise set of conditions that your body has been calibrated to over 4 billion years of evolution. Conditions that, from inside those conditions, you cannot even feel. Right now, as you read this, you are being pressed on from every direction by a force equivalent to roughly 20 tons. The atmosphere above your head, that thin, fragile shell of gas that clings to Earth's surface, is pushing down on every square inch of your body with a pressure of 14.7 pounds per square inch. That is about 101 kilopascals, if you want the scientific unit. But the number that matters is this: you feel none of it, not a gram, not a whisper. Because your body is pushing back with exactly the same force, You are a pressurized vessel perfectly matched to your environment, and you have been your entire life, and so the pressure is invisible to you. It's like asking a fish to describe water, but take that fish out of the water. Now, the absence becomes the whole story. Here's something that I think genuinely changes how you see the world once you understand it. The things keeping you alive right now are not the things you can name and point to. They're not your heart, your lungs, your immune system. Those are all downstream effects. The things keeping you alive are the environmental conditions those systems evolved inside. The pressure holding your fluids in liquid form, the oxygen partial pressure that lets your hemoglobin load and unload correctly, the magnetic field deflecting the high-energy particles that would otherwise be threading through your DNA right now, the ozone absorbing the ultraviolet radiation that would otherwise be damaging the proteins in your eyes, the temperature gradient that keeps liquid water stable on the surface of a planet. These are not background conditions. They are the machinery. Your body is not the machine, it is the passenger. And when the machine stops, the passenger has about 90 seconds before things become irreversible. Hollywood got almost everything wrong. Let's go through the list quickly, because it's worth clearing the air before we build the real picture. In movies, exposure to space causes one of two things. Either you explode skin stretching, body swelling grotesquely until it bursts, or you freeze, slowly crystallizing into a rigid corpse as the cold of space takes you. Both of these are wrong in ways that are almost poetic in their inaccuracy. The human body does not explode in vacuum. Your skin is actually quite elastic and strong enough to contain the modest internal pressure differential involved. You swell, yes, but more like a slightly overfilled balloon, not like a bomb, and you do not freeze quickly. In fact, in sunlight, you might overheat. In shade, you would lose heat only through radiation, which is a glacially slow process compared to conduction or convection. Actual freezing would take hours. You would be long dead from other causes before cold became your problem. The real process is quieter, stranger, in some ways more unsettling. Jim LeBlanc described his last few seconds of consciousness as a feeling of water bubbling on his tongue and a strange sensation of cold spreading across his skin. He did not describe pain, he did not describe terror. The body, it seems, does not rage against the removal of the atmosphere. It simply begins to malfunction, quietly and efficiently, like a program running out of memory. The saliva bubbles because at low enough pressure, water boils at body temperature. The cold sensation comes from moisture evaporating off his skin, drawing heat away as it goes. These are not violent events, they are thermodynamic events. Physical processes following equations that don't know or care that there's a human attached to them. And here is where the real vertigo sets in. None of this happens only in space. The altitude at which human blood begins to boil what scientists call the Armstrong limit is about 19 kilometers above sea level. 19 kilometers. The cruising altitude of a commercial aircraft is about 11 to 12 kilometers. That means the difference between you sitting comfortably in a pressurized airplane cabin and your blood beginning to undergo a phase transition is less than 8 kilometers of altitude, less than 5 miles. The universe's tolerance for human biology is not measured in light years, it is measured in miles. And we have built almost all of human civilization well within that margin, which is why it's so easy to forget the margin exists. The history of understanding this goes back to the early days of high-altitude aviation and the experimental chambers that engineers used to simulate altitude. The United States Air Force and NASA ran extensive tests in altitude chambers throughout the 1950s and 60s, pushing the boundaries of what they knew about human physiology at low pressure. Most of those tests involved gradual decompression, controlled conditions, observers with their hands on the controls. But what they found again and again was a body with almost no tolerance for the removal of pressure. Consciousness collapsed fast. Judgment collapsed faster. often without the subject realizing it was happening. Pilots in decompression tests would sometimes become euphoric, convinced they were fine, while the people watching them could see the cognitive decline happening in real time. And this is why the story of Jim LeBlanc matters not as an anecdote but as data. Because what happened to him in that Houston chamber in 1966 was not a near miss with something exotic and distant. It was a near miss with the same physics that governs a bad day 11 miles above your head. Space is not a special category of danger. It is an extreme point on a continuum that begins at altitudes you could theoretically reach on a very tall mountain and extends outward to the edge of the observable universe. The rules are the same everywhere. Only the severity changes. We're going to track that severity across the next several hours. We're going to go from seconds, the 14-second cascade of what happens to an unprotected human body in vacuum, to minutes, in the form of real accidents that killed real people in real spacecraft. And then we're going to slow down and look at the threats that don't kill you in 90 seconds, but in 30 years. The radiation that accumulates in your bones and your DNA. The microgravity that teaches your skeleton it doesn't need to be strong anymore. The cosmic rays that, if the current research is correct, may begin to rewire the architecture of your brain during a long mission to Mars. And at the very end, we're going to pull back far enough that the question changes entirely. Because when you understand all of this, when you've walked through every mechanism of failure, every timeline, every failed engineering solution, the question is no longer, why can't humans survive space? The question becomes something stranger and, in some ways, more important. Why does this planet exist at all? But we're getting ahead of ourselves. Let's start with the pressure you've never felt. The 20 tons of atmosphere sitting on your shoulders right now, doing a job so important and so perfectly that you have never once in your entire life thought to thank it. Part 2. The pressure you've never felt. There is a thought experiment that atmospheric scientists sometimes use to make the invisible visible, and it goes like this. Imagine you are standing at the bottom of an ocean, not a metaphorical ocean, an actual ocean of fluid, pressing down on you from all sides with the weight of everything above you. Now imagine that ocean is not water but air, and it extends upward for roughly 100 kilometers above your head, thinning as it goes until it fades into the near vacuum of space. That is what you are always standing at the bottom of. You are always a deep-sea creature. The surface of the Earth is the deepest part of the atmosphere, and we forget this only because the ocean we live in is invisible, and we've never known anything different. The pressure at the bottom of this invisible ocean at sea level, where most of us live, is approximately 101 kilopascals. In older units that engineers still use, that's 14.7 pounds per square inch. And what that means, when you translate it into terms that hit a bit harder, is that the atmosphere is pressing on every square centimetre of your body with a force of about 1 kilogram. When you add that up across the full surface area of an adult human body, roughly 1.7 to 2 square metres, you get a total force somewhere in the range of 17 to 20 metric tons. 20 tons, pressing on you all the time, from every direction simultaneously. The reason you don't feel any of this, the reason you're not crushed, is that your body is pressing back with exactly the same force. Your circulatory system, your cellular fluid, the air in your lungs, the fluid in your joints, all of it is pressurized to match the external environment. You are not a rigid object resisting pressure from outside. You are a pressurized system in perfect equilibrium with your surroundings. And that equilibrium is so complete, so total, that it produces no sensation whatsoever. The pressure is not something you feel. It's something you are. Now here's the problem. That equilibrium is only an equilibrium because Earth provides the external side of it. The atmosphere pushes in, your body pushes back, and the two cancel each other out perfectly. But what happens if you remove the atmosphere's side of the equation? What happens if the external pressure drops? The answer is that your body, which was designed to be in balance with 1 atmosphere of external pressure, suddenly has internal pressure with nothing pushing back against it. And things that need external pressure to stay in their proper physical state start to change state. The most important of these things for keeping you alive in the short term is the gas dissolved in your blood and tissues. Here's the physics. Gases dissolve in liquids more readily at higher pressures. This is why a carbonated drink stays fizzy in a sealed bottle. The carbon dioxide is dissolved into the liquid under pressure and immediately starts releasing bubbles when you open the bottle and drop the pressure. Your blood is doing the same thing continuously with oxygen and carbon dioxide and nitrogen. At normal atmospheric pressure, these gases stay dissolved in solution, but reduce the pressure fast enough and they come out of solution. They form bubbles. Inside your blood vessels, inside your tissues, inside your joints. This process is called ebulism, and it is as unpleasant as it sounds. But there's a more immediate problem than the dissolved gases. There is the vapor pressure of water itself. Water boils when its vapor pressure equals the surrounding atmospheric pressure. At sea level, where atmospheric pressure is high, water boils at 100 degrees Celsius. Everyone knows this. But as pressure decreases, the boiling point decreases too. By the time you reach an altitude of about 19 kilometers still inside Earth's atmosphere, still technically on the planet, the atmospheric pressure has dropped to approximately 6.3 kilopascals. And 6.3 kilopascals is precisely and exactly the vapor pressure of water at 37 degrees Celsius. 37 degrees Celsius is normal human body temperature, which means that at 19 kilometers altitude well below the edge of space, well within the bounds of the planet, the water in your body exists at the exact threshold of boiling. This altitude has a name. It is called the Armstrong limit, named after Harry George Armstrong, a United States Air Force flight surgeon who identified it in the 1940s. And it represents something extraordinary. It is the altitude above which an unprotected human body cannot function, not because of the cold, not because of the lack of oxygen, but because the fluids in your body begin to undergo a phase change. Your blood does not boil in the dramatic steaming sense, but the dissolved gases come out of solution, and the moisture on the surfaces of your lungs and eyes and mouth begins to vaporize. You begin, at a cellular level, to become incompatible with your own biology. 19 kilometers. Let that number sit with you for a moment. The cruising altitude of a commercial passenger jet is about 10 to 12 kilometers. The Armstrong limit is 19. The difference between you watching a movie on a transatlantic flight and the threshold at which your body fluids begin to change phase is roughly 7 kilometers. 7 kilometers of altitude. That's less than 5 miles. It is, in the grand scheme of astronomical scales, an absurdly thin margin. It is a margin that exists only because we have engineered the inside of that aircraft to maintain something very close to sea level pressure. And this is actually a point worth pausing on, because it connects directly to what we're really talking about when we talk about surviving space. The airplane is not giving you air, it's giving you pressure. The oxygen is almost secondary aircraft cabins are pressurized to a lower altitude equivalent, typically around 2,000 meters, which is why the air in a plane feels slightly thin, but what keeps you functional is the pressure. What prevents the fluid in your lungs from boiling is the pressure. The atmosphere's single most important gift to human biology is not the oxygen itself, although we need that too. It is the pressure that keeps all of your chemistry happening in the liquid phase instead of the gas phase. When engineers design spacecraft and spacesuits, the hardest thing they have to solve is not where to get oxygen from. Oxygen is a solved problem. You can carry it in tanks, you can generate it through electrolysis of water, you can recycle it in a closed-loop system. The hard thing is maintaining pressure, because maintaining pressure means containing a pressurized volume against the vacuum of space, which means every seal, every joint, every valve in your suit or your spacecraft is a potential failure point. And as we'll see in a moment, failure points in pressurized systems have a habit of finding the absolute worst possible moment to fail. The history of altitude chamber experiments at NASA and the Air Force in the 1950s and 60s reads like a catalogue of the human body's fragility at low pressure. Engineers and medical staff would put volunteer subjects, often military personnel, into chambers and gradually reduce the pressure, monitoring their responses. What they found was a pattern that repeated with uncomfortable consistency. First, subjects would notice tingling in their fingers and toes, then a sense of being very slightly drunk, then a strange, drifting contentment, a feeling that everything was fine, that the test was going well, that there was no need to worry about anything. And that feeling, that comfortable, unreliable feeling that everything is fine, is itself a symptom of hypoxia. The brain, running out of oxygen, loses first its capacity for concern. Alarm, it turns out, is a luxury. When the brain starts to go, it gives up anxiety before it gives up anything else. Which means the most dangerous phase of oxygen deprivation is the one where the subject is convinced they are doing well. Flight surgeons call this the time of useful consciousness, and the numbers are sobering. At 40,000 feet, well below the actual edge of space, well within the range of military aircraft operations, the time of useful consciousness is somewhere between 9 and 30 seconds, depending on the individual and how rapidly the decompression occurs. At 50,000 feet, it's under 10 seconds. At 60,000 feet, it's around 3 to 5 seconds, fast enough that a pilot would lose the ability to act before they fully understood what was happening. At the edge of space, effectively zero. Now here's the thing that should really make you think. These thresholds are not hypothetical. They are not theoretical. They have been measured, repeatedly, on real human volunteers in controlled environments. And what they show, without exception, is that the human body's dependency on atmospheric pressure is not a matter of degree. It is a binary. You are either inside the pressure envelope or you are not. And if you are not, the clock starts immediately. Not from the moment you notice something wrong, from the moment the pressure drops. The timer does not care about your awareness. Which brings us to what actually happens during those seconds. Because the cascade of events that unfolds when a human body meets vacuum is specific, sequential, and inevitable. And it has been documented not just in chambers, but in actual accidents with actual human beings. The mechanics of the 14-second window are not a prediction, they are an observation. And they are, in the most clinical sense of the word, remarkable. Part 3. The 14-second cascade. 0 seconds. That is the starting point. Not the moment you realize something is wrong. Not the moment you feel the first symptom. 0 seconds is the moment the pressure drops. And from that precise moment, your body begins a sequence of events that follows the same script every time, for every human, regardless of fitness or age or how much you had for breakfast. The universe is not interested in your individual particulars. At 0 seconds, if there is air in your lungs and you are holding your breath, you have immediately created a serious problem. The air inside your lungs is at higher pressure than the environment around you, and your lungs will expand to try to equalize. If you're talking about a slow decompression, a gradual leak, not a catastrophic rupture, your lungs can manage this. But in a rapid, explosive decompression, the expansion happens faster than tissue can accommodate, and you can suffer pulmonary barotrauma, essentially. Your lungs tear from the inside. This is why the first thing they tell you when you're diving is, never hold your breath. And it is why, in vacuum decompression accidents, having your mouth open and letting the air escape is actually the right instinct, even though it feels completely wrong. The air needs to get out let it go. So we're at 0 seconds. Air is leaving your lungs, either controlled or explosively. The pressure around you is dropping toward vacuum. What comes next? 1 to 2 seconds. The dissolved gases in your blood and tissues start to come out of solution. Remember the carbonated drink analogy, the carbon dioxide that stays dissolved under pressure and bubbles up when you open the bottle. Your blood is doing that now, but it's not just carbon dioxide. It's nitrogen, which makes up a large fraction of the gas dissolved in your body under normal conditions, and it's oxygen and its other gases. Small bubbles begin to form in your venous blood, in your joint fluid, in the tissues of your muscles and organs. This process will continue and worsen as time goes on. It is the same process that causes decompression sickness in scuba divers who surface too quickly, what divers call the bends, except that in vacuum, it happens orders of magnitude faster and reaches orders of magnitude greater severity. There is no slow ascent here. There is no time to off-gas gradually. The pressure went from 1 atmosphere to essentially 0 in a fraction of a second. 2 to 5 seconds. Your soft tissues begin to swell. This is the moment that the movies get half right. The body does expand, but it doesn't explode. The skin is elastic enough and tough enough to contain the swelling without rupturing under the pressure differential involved in vacuum exposure. What you get is a bloated, distorted appearance, the tissue swelling caused by gas formation and fluid redistribution, but not the dramatic rupture of Hollywood. Jim LeBlanc, after his chamber incident, reportedly swelled up noticeably before being repressurized and recovered without major physical injury. The skin holds. What doesn't hold as well is the internal pressure in the small blood vessels near the surface, which is why you also start to see another process beginning tiny ruptures in the smallest capillaries, which will leave characteristic marks on the body visible in autopsy. 5 to 9 seconds. Something strange happens. You feel cold. Not because space is cold, the heat conduction problem we discussed earlier is still in play, and you're not losing heat quickly enough through radiation for the cold of space to matter yet. You feel cold because moisture is evaporating off the surface of your skin, off your eyes, off the mucous membranes of your mouth and nose and lungs. And evaporation is a cooling process. Every molecule of water that transitions from liquid to vapor takes energy with it, and that energy comes from your surface temperature. Jim LeBlanc reported this sensation explicitly, the bubbling, cooling feeling on his tongue, the evaporation of saliva. The body is, in a sense, sweating itself dry in seconds, and the cooling that results is exactly the same cooling you feel when you step out of a swimming pool on a breezy day, scaled up to an almost surreal intensity. This is also the moment when the moisture in your lungs is vaporizing, not boiling in a heat sense, remember. It's the pressure driving this, not the temperature, but transitioning from liquid to gas phase. The efficiency of gas exchange in your alveoli, which depends on a thin film of liquid on the surface of the lung tissue, collapses. Even if there were oxygen around you, your lungs could not absorb it properly. The machinery of respiration is failing from the inside. 9 to 14 seconds. This is the window that Jim LeBlanc was at the far edge of when the chamber was repressurized. The oxygen partial pressure in your blood has collapsed. The oxygenated blood that was in your brain when the decompression started has been consumed by your neurons, and there is no resupply coming. Your brain begins to shut down non-essential functions first, a triage process that happens below the level of consciousness. You don't choose what your brain deprioritizes. It makes those decisions without you. And somewhere in this window, your eyes close, your muscles relax, and you lose consciousness. Not with pain, not with drama, with the quiet efficiency of a system that has run out of what it needs to run. 14 seconds. That's the number. That's the edge of the useful window. After that, you are not making decisions anymore. You are not calling for help. You are not reaching for the airlock. You are a body, unconscious, beginning the final stage of a process that has no good outcomes without immediate external intervention. 15 to 60 seconds. Your heart is still beating, but it is losing the circulatory support it needs to do so effectively. The blood that was carrying oxygen is no longer carrying oxygen efficiently. Cardiac output begins to fall. The rhythm, initially maintaining itself on the residual electrical signals from your heart's own internal pacemaker, begins to become erratic. Arrhythmias start. The circulation that was keeping your brain oxygenated, even if only barely, begins to falter further. Any chance of intervention that restores full function is narrowing with every passing second. 60 to 90 seconds. The brain damage that begins in this window is, at current medical understanding, considered irreversible. The neurons that power consciousness, memory, and personality are extraordinarily sensitive to oxygen deprivation, and 90 seconds without adequate oxygen supply is enough to begin destroying them permanently. This is not a recoverable condition. Even if you were repressurized at 91 seconds, even if your heart was restarted and your circulation restored, the brain you came back with would not be the brain you left with. Something essential, and the research on exactly what is still ongoing would be different, changed, gone. 90 to 180 seconds. Death. And again, not the death of movies, not convulsions and dramatic final words, the death of a system running out of power, quiet, predictable. The same way every time. Here's the thing about this timeline that doesn't get said enough. It is not theoretical. These are not extrapolations from animal models or worst-case projections by cautious scientists. This cascade has been observed. Parts of it have been lived through and described, as Jim LeBlanc described the early seconds. Parts of it have been inferred from the physical evidence left on bodies that didn't make it through the early seconds. And the remarkable thing, the thing that makes this information genuinely unsettling in a way that mere statistics can't, is how universal it is. Fitness doesn't help you. Youth doesn't help you. Training doesn't help you. The timeline is the timeline. The physics don't negotiate. And we know this with a particular, terrible certainty because of what happened in June of 1971 at an altitude of 168 kilometers above Earth inside a spacecraft that was otherwise functioning perfectly. 3 men went through this cascade, or something very close to it, in complete isolation, with no one who could repressurize anything in time. Their autopilot brought them home. When the recovery team opened the capsule, the cosmonauts of Soyuz 11 were sitting in their seats, showing no signs of external trauma, looking as though they had simply fallen asleep. They had been dead for hours. Part 4. The only humans who died in space. Georgy Dobrovolsky was the commander. Vladislav Volko was the flight engineer. Viktor Patsayev was the research engineer. They were the crew of Soyuz 11, and they hold a distinction that, as of everything we know today, remains unique in human history. They are the only people to have died above what is internationally recognized as the boundary of space. They did not die on the way up. They did not die in a fire or an explosion. They died on the way home, sitting in their spacecraft, during the routine depressurization of the re-entry sequence, because a valve failed. The story begins with what should have been a triumph. Soyuz 11 launched on June 6, 1971, and successfully docked with Salyut 1, the world's first space station, launched just over a month earlier. The crew spent 23 days aboard the station, setting a new record for the longest human spaceflight to that point. They conducted scientific experiments. They broadcast television transmissions back to Earth. They were heroes of the Soviet space program, riding what felt like a wave of genuine achievement. The return, on June 29th, began normally. The crew prepared for re-entry, undocked from the station, and began the sequence that would bring them home. The Soyuz spacecraft, by design, separated into modules during descent, the orbital module detaching from the descent capsule, which would carry the crew through the atmosphere. And it was during this separation that the mission ended. The separation of modules was supposed to trigger a series of pyrotechnic bolts, small explosive charges that would fire in sequence, separating the connected sections cleanly. What appears to have happened is that both sets of bolts fired simultaneously instead of in sequence. The shockwave from this combined firing traveled through the spacecraft and forced open a pressure equalization valve, a small 1 centimeter valve designed to allow the cabin pressure to gradually equalize with the external atmosphere during the final stages of descent. When the capsule was much lower in the atmosphere and the outside pressure would be approaching sea level at an altitude of 168 kilometers, that valve opened. The cabin pressure at that altitude equalized almost immediately with what was outside, essentially nothing. The cosmonauts had approximately the same window that Jim LeBlanc had inside that Houston chamber in 1966. 14 seconds of useful consciousness, give or take. But, unlike LeBlanc, there was no technician at a control panel. There was no one who could push a button and repressurize the cabin. The valve was later found to have been a manual closure physically reachable by the crew, but the location of it, the speed of the decompression, the loss of consciousness that came before there was time to find and close it, all of it conspired against them. By the records that were later reconstructed, Patsayev may have partially reached the valve and begun to close it before losing consciousness. It was found partially closed, as though someone had started the motion and then stopped. 14 seconds is not long enough to find a valve you've never had to find under emergency conditions. Identify the correct direction to turn it and turn it far enough to seal. The autopilot, which needed no oxygen and felt no pressure, continued to function perfectly. The re-entry sequence proceeded as designed. The parachutes deployed. The retrorockets fired at the correct altitude. The capsule came down gently. The recovery team that reached it expected to find 3 cosmonauts ready to be helped out of their seats. What they found instead told them immediately that something was wrong. There was no movement through the porthole. There was no response to knocking. When they opened the hatch, the 3 men were sitting in their couches in their correct positions, showing no signs of violent trauma, their faces composed and seemingly peaceful. They had the characteristic appearance of men who had lost consciousness suddenly and without warning, which is exactly what had happened. Resuscitation was attempted immediately and was unsuccessful. They had been dead for roughly 30 minutes by the time the capsule landed. The autopsies confirmed what the physics had already told us would be true. The cause of death was listed as hemorrhage and asphyxia from decompression. Internally, there was evidence of gas bubble formation in the tissues. There were petechial hemorrhages, tiny, characteristic pinpoint bleeding marks left when small blood vessels rupture on the skin and in the eyes. Nitrogen had come out of solution in their blood. Their lungs showed the effects of rapid decompression. Everything that the 14-second cascade predicts was confirmed in the post-mortem evidence. The physics did not make an exception for heroes. There is a detail of this story that has always struck me as particularly poignant, and I want to make sure it lands correctly. The 3 men of Soyuz 11 were not wearing pressure suits. They were in ordinary flight suits coveralls, essentially. And this was not an oversight. It was a deliberate engineering decision, made because the Soyuz capsule at that time could only seat 3 people if pressure suits were not worn. The suits took up too much space, and so a trade-off was made. The capsule design was considered reliable enough that pressure suits, which would be the one layer of protection between a crew and exactly this kind of failure, were deemed unnecessary. The valve that killed them was designed to operate low in the atmosphere. It was not designed to be vulnerable at 168 kilometers. The failure mode was considered implausible enough to not design against. Every single Soyuz mission after Soyuz 11 has required the crew to wear pressure suits during launch and re-entry. The policy was not implemented because the engineers had not thought of it before. It was implemented because the engineers now had data they had not previously had, paid for in the only currency that kind of data is ever purchased in. This brings us back to the central question, with something sharper than abstract theory can provide. The 3 cosmonauts of Soyuz 11 were inside a spacecraft. They were in a controlled environment. They had life support. They had communication with Earth. They had 23 days of successful operation behind them, and a valve the size of a coin killed all 3 of them in under 2 minutes, because between them and the vacuum was exactly 1 layer of engineered protection, and that layer failed. The margin between a living human being and the physics of vacuum is always and only as wide as the engineering that creates it. And here is where the story gets even more complicated. Because sometimes the engineering that creates an environment to protect human life creates, in the process of doing so, a new kind of danger that no one anticipated until someone died. Part 5. The Environments That Turn Deadly. On January 27th, 1967, 3 American astronauts, Virgil Grissom, Edward White, and Roger Chaffee, died on the launch pad at Cape Canaveral, Florida, inside the Apollo 1 command module, during what was supposed to be a routine pre-launch test. They never left the ground. They never experienced vacuum. They died from a fire that started inside the spacecraft and spread with a speed and ferocity that caught everyone off guard. And the reason the fire spread so fast, the reason what should have been a containable emergency became a fatal one in seconds, was the atmosphere. The Apollo command module was pressurized for the ground test with pure oxygen at a pressure slightly above sea level, 16.7 pounds per square inch, in an environment of pure oxygen. Now, here's the thing about oxygen concentration and fire. In normal air, roughly 21% of the gas is oxygen. That's enough to support combustion. Obviously, fires happen all the time in normal air. But the rate at which fire spreads and the range of materials that will burn depend critically on the oxygen concentration. At 100% oxygen, at above ambient pressure, materials that would be completely safe in normal air become highly flammable. Metals burn. Nylon burns. Velcro, which was extensively used in the interior of the Apollo capsule, burns. The whole interior of the spacecraft became, in a pure oxygen environment, a collection of potential fuels waiting for an ignition source. A spark the exact origin of which was never definitively established provided that source. What followed took approximately 17 seconds. The fire spread so rapidly through the oxygen-rich environment that the crew had no time to open the hatch, which opened inward and required multiple steps to operate under the best conditions. The pressure inside the cabin rapidly exceeded the outside pressure as the fire consumed oxygen and heated the air, making the hatch even harder to open. All 3 astronauts died of smoke inhalation and burns within seconds of the ignition. The fire burned through the hull in seconds. This connects to the central problem we've been tracing in a way that's worth making explicit. The engineers who designed the pre-launch test atmosphere were trying to solve one problem: creating a life-sustaining environment inside the spacecraft. They succeeded at that. The oxygen kept the crew alive, but in creating an atmosphere, they inadvertently created a new failure mode that was worse than the one they were guarding against. The solution to the vacuum introduced the risk of the fire. You cannot remove all the risks. You can only trade them. What makes this pattern even more striking is that less than a month before the Apollo 1 fire, a young Soviet Air Force trainee named Valentin Bondarenko died in almost identical circumstances. Bondarenko was completing a 10-day isolation endurance test inside a pressurized chamber at the Institute of Aviation and Space Medicine in Moscow. The chamber was pressurized with oxygen. At the end of a testing session, Bondarenko removed medical sensor pads from his skin and carelessly discarded an alcohol-soaked cotton swab, which landed on an electric hot plate. The fire that resulted in that oxygen-rich environment was instantaneous and total. Bondarenko suffered burns over most of his body and died about 16 hours later. He was 24 years old. The Soviet Union kept Bondarenko's death secret for decades. The American engineers who designed the Apollo 1 test did not know about it. Two space programs, on opposite sides of the most intense technological competition in history, made the same assumption about oxygen environments, and both paid for it within weeks of each other in January and February of 1967. The knowledge that might have saved the Apollo 1 crew existed, somewhere in Moscow, but the secrecy of the Soviet program kept it from reaching the people who needed it. Both disasters reinforce the same point. The problem of surviving space is not just the problem of surviving vacuum. It is the problem of maintaining life in an artificial environment where every engineering decision that solves one problem potentially creates another. The vacuum requires pressure. The pressure requires a contained atmosphere. The contained atmosphere changes the fire behavior of every material inside it. And the faster you try to build and test and iterate under competitive pressure, whether political or professional, the higher the chance that you miss a failure mode until the failure mode introduces itself. And if the environment inside the spacecraft can kill you, what about the suit you're wearing when you leave it? Part 6. The suit is not safety. On July 16, 2013, Italian astronaut Luca Parmitano was about 90 minutes into a spacewalk outside the International Space Station when he noticed something unusual. There was water inside his helmet. Not a worrying amount, at first a small quantity, enough to notice but not enough to cause immediate alarm. He informed Mission Control and they discussed it. The assessment was that it was likely sweat. The spacewalk continued. It was not sweat. Over the next several minutes, the water began to accumulate, not dripping from a surface the way water behaves in gravity, but forming a blob, a free-floating sphere of water that, in microgravity, was not falling anywhere. It was gathering. It migrated from the back of his helmet, where it had first appeared, toward the front. It began to obscure his vision. The communication ports inside the helmet, the small openings through which sound traveled to and from his earpieces, began to fill. His ability to hear Mission Control degraded. His vision, with water pressing against his eyes, degraded. He could not wipe his eyes because he was inside a sealed helmet in vacuum. The water was coming from his suit's cooling system, the system that regulated the temperature inside the suit, because without active cooling, the heat generated by an astronaut's body has nowhere to go in vacuum, and the suit would become lethally hot had sprung a leak. Water was flooding into the inside of the helmet. Here, in vacuum, a substance that is completely benign, that your body is mostly made of, that you need to survive, was becoming a direct threat to your life. In microgravity, there is no down for the water to drain. It collects where surface tension takes it. It fills the spaces it can reach. And the space it was reaching was the interior of the sealed helmet through which Luca Parmitano was trying to breathe and see and navigate his way back to safety. By the time the decision was made to end the spacewalk and return to the airlock, Parmitano could barely see. He navigated back to the ISS airlock. Largely from memory, he had done enough spacewalks to know the layout, the handholds, the path. He found the airlock. He got inside. The hatch closed. Repressurization began. And when his crewmates removed his helmet, they found so much water inside it that it was sloshing. It had covered his nose. It had been accumulating over his face. He had been, as he described it afterward, effectively drowning in vacuum outside a space station, in a suit designed to keep him alive. The suit is not armor. The suit is a life support system. It is a pressurized volume with an oxygen supply and a thermal regulation system and a communication system and a waste management system and a power supply and 100 other subsystems, each of which is a potential failure point. And the lesson of Parmitano's near miss is the same lesson as Soyuz 11, the same lesson as Apollo 1. Between a human being in space and the physics of space, there is always only engineering. And engineering is what it is. It works until it doesn't. Parmitano survived. He's still an astronaut. He's been back to the ISS, but the water in his helmet was, quite literally, millimeters from his nose when the airlock was repressurized. The margin was not technical, the margin was personal. And it illustrates, with almost uncomfortable clarity, that every human being who has survived in space has survived not because space was manageable, but because the engineering held long enough. Take any single crewed mission across the entire history of human spaceflight and trace every near miss that could have ended it, and you begin to understand that the history of humans in space is, in many ways, a history of things that almost went wrong but didn't. Which brings us to the dangers that don't announce themselves with a beeping alarm and a visible problem and a window to act. The ones that are happening right now to astronauts aboard the International Space Station, silently, invisibly, accumulating in the tissues and the DNA and the architecture of the brain. The ones that don't kill you in 2 minutes, but in 20 years. And the ones that, if we ever try to go to Mars, will be the defining challenge of the mission in ways we are still struggling to understand. Part 7. The radiation you cannot feel. Here is something happening to your body right now that you will never feel and cannot stop. High-energy particles, protons, helium nuclei, and heavier atomic nuclei stripped of their electrons and accelerated to relativistic speeds are passing through your body at this moment. Some of them are coming from the sun. Others are coming from supernovae that exploded thousands or millions of years ago in other parts of our galaxy, or from outside the galaxy entirely. These particles are called cosmic rays, and they have been raining down on every living thing on Earth's surface since life first appeared here. They are part of the background radiation of the universe, not a special threat, not a targeted beam, just the ambient energy environment of a cosmos that is very, very active on scales that dwarf anything happening on this planet. And here is the thing. You are not experiencing their full force. You never have. What you are experiencing is a tiny fraction of what actually arrives at the top of Earth's atmosphere, filtered through 2 layers of protection that you have never had to think about because they have always, without exception, been there. The first layer is the magnetosphere. Earth has a magnetic field generated by the churning of molten iron in its outer core, and that field extends far out into space, forming a vast teardrop-shaped bubble that deflects a significant portion of the charged particles streaming outward from the sun, what's called the solar wind, around the planet rather than through it. Without the magnetosphere, the solar wind would strip away Earth's atmosphere over geological timescales, as it has stripped away the atmosphere of Mars, which lost its magnetic field billions of years ago. With it, the most energetic charged particles from the sun are bent away from us, and only a fraction of the cosmic ray flux actually makes it into the upper atmosphere. The second layer is the atmosphere itself. When a cosmic ray particle that has made it through the magnetosphere hits the upper atmosphere, it doesn't simply pass through unchanged. It collides with molecules of nitrogen and oxygen and triggers a cascade of secondary particles, a shower of lower energy products that spread out as they travel downward. By the time these products reach sea level, the radiation dose they deliver is a small fraction of what the original particle carried. The atmosphere has functioned as a particle physics shield for your entire life, and like the pressure and the oxygen and the temperature regulation, it has done this job so consistently that you have never had to know it was doing it. Now take that shield away. On the International Space Station, which orbits at about 400 kilometers above sea level, above the bulk of the atmosphere, though still partially within the protection of the magnetosphere, the radiation environment is roughly 150 to 200 times higher than at Earth's surface. Astronauts on the ISS receive a radiation dose of about 1 millisievert per day, compared to about 2 millisieverts per year at sea level. Over a 6-month mission, a typical ISS crew member accumulates roughly the equivalent radiation exposure that a person at sea level would receive over decades. It's not immediately lethal, it's not acutely dangerous, but it accumulates. And what it accumulates into is a meaningfully higher lifetime risk of cancer. NASA has calculated that a Mars mission accounting for the transit time each way, which the Curiosity rover's radiation assessment detector measured at approximately 1.8 millisieverts per day during its cruise to Mars, would expose a crew member to a total mission dose of somewhere in the range of 600 to 1,000 millisieverts, depending on solar activity and shielding. That translates to an estimated 3 to 5% increase in lifetime cancer risk, over and above the baseline risk every human carries. 3 to 5% may not sound like a large number, but it is a large enough number that NASA's current radiation exposure limits for astronauts, which are set based on what the agency considers an acceptable career radiation risk, would be exceeded by a Mars mission under current technology. The mission is, technically, outside the safety envelope by the metric of cancer risk alone. But cancer is the risk we understand. It is the risk we can calculate with reasonable confidence because we have decades of data from medical radiation exposures, from atomic bomb survivors, from nuclear workers, and from astronauts themselves. What we understand much less is what happens specifically to the brain. Because cosmic rays are not like the X-rays at your dentist's office or the gamma rays from a medical scan. Those are what physicists call low linear energy transfer radiation. They pass through tissue, depositing energy relatively gently and diffusely. Cosmic rays, particularly the particles called HZE particles, high charge, high energy, are a different category entirely. When an HZE particle passes through biological tissue, it deposits a dense track of energy along its path. It does not pass through gently. It goes through like a bullet, leaving a column of ionized molecules, broken chemical bonds, and damaged cells in its wake. And neurons, the cells that form the physical substrate of your thoughts, memories, and personality, are not good at repairing this kind of damage. Neurons are largely post-mitotic cells. They do not divide and replace themselves the way skin cells or blood cells do. When they are damaged, they tend to stay damaged. And here is the thing that makes the Mars timeline particularly concerning. The transit from Earth to Mars, depending on the orbital configuration, takes between 6 and 9 months, one way. So a crewed Mars mission involves at minimum 12 to 18 months of transit, plus however long the crew spends on the surface, plus the return transit. That is a long time to be outside the magnetosphere. A very long time to be soaking in a flux of HZE particles that your brain did not evolve to handle, because in the 4 billion years of life's history on Earth, no living thing has ever had to handle it. The magnetosphere has always been there. To give you a sense of the energies involved, and this is where the universe's contempt for human scale becomes almost amusing, consider the particle that physicists call the oh my god particle, detected in 1991 over Utah by the Fly's Eye cosmic ray detector. This was a single subatomic particle, a single proton that was moving so fast, carrying so much kinetic energy, that it had the kinetic energy of a baseball pitched at about 90 kilometers per hour. Not a beam of particles, not a collection of particles. One proton, moving at 99.99999999999% of the speed of light, carrying macroscopic kinetic energy in a subatomic package. The universe creates these things, occasionally, somewhere in the cosmos, and sends them raining down on anyone not protected by a magnetic field and an atmosphere. We do not know where they come from. We do not fully understand the mechanisms that accelerate particles to those energies. We just know they happen, and that when they hit our atmosphere, they create showers of secondary particles that fan out across tens of kilometers of sky. One particle, detectable across kilometers. That is the energy environment that Earth's magnetic field and atmosphere are quietly managing on your behalf every moment of your life. Solving the radiation problem for a Mars mission is not, currently, a solved problem. Adding shielding to a spacecraft adds mass, which requires more fuel, which changes the entire engineering equation of the mission. The most effective shielding materials for cosmic rays are hydrogen-rich plastics, water, polyethylene rather than heavy metals, because the goal is to absorb and scatter incoming particles rather than cause spallation events, where the shield itself produces secondary radiation. But even the most optimized shielding reduces the dose, not eliminates it. There is, with current technology, no way to give a Mars crew the radiation protection they would have on Earth's surface. The planet is the shield, and you cannot bring the planet with you. So, the astronauts going to Mars would be making the trip knowing their radiation exposure is beyond established safety limits by cancer risk metrics, and potentially doing something to their brains that we're only beginning to understand. Let's talk about what that might mean. Part 8. The brain that doesn't come back the same. Charles Limerly is a neuroscientist at the University of California, Irvine, and he has spent years studying what happens to the brains of mice when they are exposed to the kinds of radiation that astronauts on a Mars transit would encounter. His research group at Brookhaven National Laboratory in New York, which has a particle accelerator capable of producing beams of heavy ions that simulate galactic cosmic rays, has published a series of studies that should probably be required reading for anyone planning to send humans beyond low Earth orbit. What Limerly and his colleagues found in their mouse studies was not what anyone was hoping to find. Mice exposed to simulated cosmic radiation doses, calibrated to approximate what a Mars crew would receive during transit, showed measurable changes in their brains. Specifically, they showed a reduction in the density of dendritic spines, the tiny branching projections on neurons that form the physical connections between brain cells. Fewer spines means fewer synaptic connections. Fewer synaptic connections means reduced communication between neurons. And reduced communication between neurons means reduced cognitive function. But the finding that really grabbed attention was not just the reduction in connectivity, it was the persistence of the reduction. The cognitive deficits that Limerly's mice showed problems with memory, with learning new tasks, with what neuroscientists call executive function, the ability to plan and make decisions did not go away. They were still measurable 6 months after the radiation exposure. In a mouse lifespan, 6 months is a significant fraction of the entire life. In human terms, we don't know yet what the equivalent persistence would be, because we have not conducted these experiments in humans and ethically cannot. But the fact that the effect did not diminish over time in the animal model is, to put it gently, not reassuring. Here's the mechanism, as best we currently understand it. When an HZE particle passes through a neuron, it causes direct physical damage to the cell, breaking DNA strands, damaging the cell membrane, disrupting the mitochondria. But it also causes something more diffuse, oxidative stress. The ionization of molecules along the particle's track creates reactive oxygen species, chemically aggressive molecules that spread outward from the track and damage nearby structures. This oxidative damage affects not just the neurons directly in the path, but also the supporting cells, the microglia and astrocytes that maintain the brain's chemical environment, and it can trigger a chronic inflammatory response. The brain, which normally keeps inflammation carefully regulated, begins to mismanage it, and chronic neuroinflammation is associated with cognitive decline, with memory problems, with mood disorders. It is a thread that runs through Alzheimer's disease and other neurodegenerative conditions, and finding it in the brains of mice after cosmic ray exposure is the kind of finding that gives long-duration mission planners pause. Now, here is the important caveat: mice are not humans. The extrapolation from rodent neuroscience to human cognition is always uncertain, and particularly so for something as complex as the effects of radiation on higher cognitive function. We do not know, with certainty, that human astronauts on a Mars mission will experience the same cognitive changes Limmerle's mice showed. What we know is that the biological mechanism, the pathway from radiation to DNA damage, to oxidative stress, to neuroinflammation, to cognitive effect, is the same in humans as in mice. The question is the magnitude. And we know from the astronauts who have already been to the ISS and back that something is happening. The studies are not as dramatic as the mouse data ISS crews receive less radiation in a somewhat different spectrum over shorter periods. But there are documented changes. Astronauts coming back from 6-month missions show alterations in white matter connectivity, the long-range connections between different brain regions that differ from their pre-flight scans. They show changes in the fluid dynamics of the brain, partly related to the fluid shifts caused by microgravity, but potentially also related to radiation effects. Whether these changes are permanent, whether they are large enough to matter functionally, whether they get worse with longer missions, these are questions for which we do not yet have clear answers. What we do have is a situation where we are considering sending human beings on a journey of 6 to 9 months through an environment that may measurably degrade their cognitive function, with no way to turn around and come back if problems develop, no way to bring them back quickly if something goes seriously wrong, and no medical infrastructure on either end of the journey capable of addressing neurological damage of this kind. The human body's incompatibility with space is not just a mechanical problem, a matter of seals and valves and pressure systems. It goes all the way down to the level of individual neurons and their connections, and at that level, the damage is quiet, invisible, and potentially irreversible, which leads to the equally quiet, equally invisible process happening in the rest of the body. Part 9. The body starts forgetting Earth. Here is something that should not work, and yet does, and the fact that it does tells you something important about how precisely calibrated the human body is to Earth's conditions. When you stand up, the blood in your legs does not pool there under gravity and starve your brain. It doesn't, because your cardiovascular system has evolved over hundreds of millions of years to actively pump blood upward against gravity, to maintain pressure in your arteries regardless of your orientation, to respond dynamically to changes in position and exertion. Your body knows what gravity is. It has always known. Every system in your body is, in some sense, designed around the assumption that there will be a 9.8 meters per second squared downward pull on everything inside you. Your heart beats with a particular rhythm calibrated to that pull. Your veins have one-way valves positioned specifically to prevent backflow in a gravitational field. Your inner ear has tiny calcium crystals that drift in a specific direction under gravity and tell your brain which way is down. You are, from the molecular level all the way up to the organ level, a gravity machine. A one-gravity machine, specifically. Not half a gravity, not 2 gravities, one. This one planet's one. Take away gravity, and those systems keep doing what they were designed to do in gravity. And that, it turns out, is a problem. In microgravity, the blood that your cardiovascular system has been trained over evolutionary time to fight against pooling in your legs no longer needs to be fought. There are no legs to pool in any meaningful fluid dynamic sense, because there is no gravitational pull drawing fluid downward. So the blood redistributes. It moves toward the upper body and the head, because there is no gravity pulling it down, and the cardiovascular system is still pushing it around with the same pressure it always used. Astronauts on the International Space Station describe a persistent feeling of fullness in the head, a stuffiness, a pressure behind the eyes, that resembles having a mild head cold and never quite goes away. Their faces become puffy and rounded. Their legs, deprived of the fluid that used to pool in them, become thinner and somewhat wasted-looking, even early in a mission. They look, as the astronauts themselves have noted with what I think is admirable self-awareness and humour, like they are slowly turning into lollipops, round head, thin legs. The body reshaping itself, in response to an environment it was never meant to inhabit. This fluid shift has consequences, and not all of them are cosmetic. One of the most concerning is what it does to the eyes. The redistribution of fluid toward the head increases the intracranial pressure, the pressure of the cerebrospinal fluid that surrounds the brain and spinal cord, cushioning it and regulating its chemical environment. Increased intracranial pressure pushes on the optic nerve, which passes through the back of the eye in a bony channel and connects the retina to the brain. The optic disc, the point where the nerve enters the eye, can become swollen, a condition called papilledema, but it goes further than that. The rear of the eyeball can actually change shape, flattening slightly under the sustained pressure from behind. The lens, the vitreous humor, the retina, all of them shift when the geometry of the eyeball shifts. And these structural changes cause vision problems that range from mild blurring of near or distant objects to significant impairment of visual acuity that does not fully correct with glasses because the problem is not a refractive error. The problem is a reshaped eye. This syndrome has a name: Spaceflight-Associated Neuroocular Syndrome, or SANS, and it has emerged as one of the most significant and least solved health concerns for long-duration spaceflight over the last decade of serious research. It affects a substantial fraction of astronauts on missions of 6 months or longer, and what makes it particularly unsettling is that we do not yet have a reliable way to prevent it. Exercise does not fix it. Fluid restriction does not reliably fix it. Lower body negative pressure devices, essentially vacuum pants, that pull fluid back down toward the legs show some promise, but are not a complete solution. For a Mars mission, where astronauts would spend 6 to 9 months in transit before even arriving, SANS represents a genuine open problem. You could send a crew to Mars and have them arrive with meaningfully degraded vision and elevated intracranial pressure before the surface mission has even begun. Scott Kelly, who spent 340 days on the ISS as part of NASA's twin study, a study comparing him to his genetically identical twin brother Mark, who remained on Earth as a living control subject, showed significant changes in gene expression, cognitive performance, and the physical structure of his eyes. Some of those changes persisted for months after his return. Some, years later, have not fully reversed. Mark Kelly, on the ground, on Earth, inside the atmosphere and the gravity field, and the full protection of the planet's magnetic field, showed essentially none of the same changes. The comparison is about as clean as human biology ever gets. Same genes, same upbringing, same professional training, different planet, different body. And while the fluid shift is doing its visible, measurable work on the visual system, something quieter is happening in the bones, and muscles quieter only in the sense that you cannot see it happening, not in the sense that it is less serious. Bone density in a healthy person on Earth is maintained by a constant, ongoing process of remodeling. Old bone is broken down by cells called osteoclasts, and new bone is deposited by cells called osteoblasts. These two processes balance each other in a dynamic equilibrium that is directly responsive to mechanical loading. When you walk, when you run, when you carry weight, the mechanical stress on your bones sends a signal mediated by specific bone cells called osteocytes that detect strain, that tells the remodeling system to maintain or increase density. Your bones know they are being used, and they invest in the infrastructure accordingly. It is, when you think about it, a beautifully efficient system. The body does not build bone it doesn't need. It builds exactly as much as the mechanical environment demands, which is fine until the mechanical environment stops demanding anything. Take away the mechanical loading, as happens in microgravity, where the skeleton bears essentially none of its own weight and no gravitational force is transmitted through the bones during movement, and the remodeling process falls badly out of balance. Osteoclasts keep breaking bone down. Osteoblasts receive no signal to replace it at the usual rate and reduce their activity. The net result is bone loss of approximately 1 to 2% per month in weight-bearing bones, the femur, the tibia, the lumbar spine, the pelvis. In a single year, that compounds to 12 to 24% of bone density. To put that in context, a postmenopausal woman on Earth losing bone to osteoporosis, a condition serious enough to warrant medical treatment and regular monitoring, might lose 1 to 2% per year. Astronauts lose that much in a single month. The rate is not comparable. It is an entirely different category of loss. Muscles follow the same logic for the same reason. Without gravity to resist, without the constant background effort of simply holding yourself upright and propelling yourself through a gravitational field, the muscles that evolved for exactly that purpose begin to atrophy. They are expensive metabolically, and the body is efficient if they are not being used. It does not maintain them at full capacity. Astronauts on long missions exercise for roughly 2 hours every day, using resistance devices and treadmills with harness systems, and this significantly reduces the rate of muscle loss. But it does not eliminate it. The exercise is fighting a slow battle against an environment that wins in the end if you stay long enough. Valery Polyakov, a Russian cosmonaut and physician, holds the record for the longest single human spaceflight, 437 days aboard the Mir space station, from January 1994 to March 1995, more than 14 months. When he returned to Earth, he insisted on walking from the descent capsule to the medical tent under his own power. He wanted to demonstrate to the watching world, and perhaps to himself, that a human being could survive 14 months in space and come back walking. He managed it, just. The effort it required was immense, and the months of rehabilitation that followed were extensive. What it showed, more clearly than any controlled study, was that 14 months in microgravity does real, serious, lasting work on a body that spent 4 billion years of evolutionary history, assuming it would never have to live without gravity for even a single day. The twins study then confirmed something even more fundamental. Scott Kelly's genome showed changes in gene expression, epigenetic changes, alterations in which genes were active and which were suppressed that were not present in his genetically identical brother on the ground. Most of these changes reversed when he returned to Earth. Lose? Some did not. His telomeres, the protective caps at the ends of chromosomes associated with cellular aging and genomic stability, lengthened during his mission, which surprised almost everyone, and then shortened faster than expected after his return, ending up shorter overall than before he left. The biological meaning of this telomere behavior is still being worked out by researchers, but the message it sends is unambiguous. Space does not merely stress the body, it changes it. At the level of which genes are being read, at the level of chromosomal structure, the body, removed from Earth's conditions long enough, does not simply function less well in the way a machine functions less well when some of its parts are removed. It begins to adapt, to become something calibrated to a different place, something that is no longer quite the same organism that left. And the question that nobody has a clean answer to, yet the question sitting at the frontier of space medicine and keeping a number of very serious researchers up at night, is whether there is a point of no return. Whether a body that has spent long enough away from Earth can fully return to what it was. And more critically, whether partial gravity, the 1/6 gravity of the Moon, the 1/3 gravity of Mars, provides enough mechanical signal to the bones and the cardiovascular system and the fluid regulation to prevent these processes from running. We do not know. No human has ever lived in 1/3 gravity long enough to find out. And the fact that we are genuinely uncertain about the answer, that there is a real possibility, not a fringe concern, but a mainstream scientific uncertainty, that partial gravity is not enough, tells you everything about how specifically and how completely the human body is built for this one planet. These exact conditions, this precise gravitational pull. Not space in general, not planets in general. Here, this one. Part 10. The closest we ever came to not dying. On April 13th, 1970, at 55 hours and 54 minutes into the mission of Apollo, 13 astronaut Jack Swigert spoke 13 words into a radio link to Mission Control in Houston. Houston, we've had a problem here. 13 words, delivered in a tone that, if you listen to the recording, is almost unnervingly calm, not panicked, not shouting. The measured, controlled voice of a trained pilot reporting an anomaly, the way you might report a warning light on a car dashboard. The tone does not match what was actually happening, which is part of what makes the recording so striking. What was actually happening was that the mission had just crossed from difficult into potentially unsurvivable, and the 3 men on board had not yet fully understood that. An oxygen tank in the service module had ruptured. The exact cause was a fault in the tank's internal heating element, the result of a design modification years earlier that had not been properly documented, combined with a ground test procedure that had unknowingly damaged the insulation on the wiring, combined with a stirring fan activation mid-mission that ignited the damaged insulation in the pure oxygen environment of the tank. The explosion that resulted had damaged a second oxygen tank and blown off an entire panel of the spacecraft's outer hull, a panel about the size of a large door, gone, tumbling away into space. 2 of the 3 fuel cells that generated electrical power for the command module were dead. The third was failing. The command module was losing power and oxygen simultaneously, at a point in the mission that placed the spacecraft roughly 200,000 miles from Earth, already well past the Moon on their outbound trajectory with 3 astronauts on board. No direct abort trajectory home, and a spacecraft that was, by any engineering definition of the word, critically damaged. Jim Lovell, the commander, looked out the window and saw a cloud of gas venting from the side of the spacecraft into space. He understood immediately what it meant. They were losing the oxygen that the fuel cells needed to generate power. They were losing the oxygen the crew needed to breathe. And they were 200,000 miles from the only place where either of those things could be replenished. The crew transferred to the lunar module, the small, spidery spacecraft designed to land 2 astronauts on the Moon's surface and bring them back up again, and used it as a lifeboat. It had its own independent life support system, its own power supply, its own oxygen. It had not been designed to support 3 people for 4 days. It had been designed to support 2 people for roughly 2 days. The power budget was almost impossibly tight. The water budget was tight. The food was whatever the crew could eat cold, without heating, to conserve power. The temperature inside the lunar module, as the crew reduced power consumption to a minimum, dropped to near freezing. The astronauts wore their suits for warmth and slept in shifts, though sleeping was difficult in the cold, in the noise, in the knowledge of what they were orbiting inside. They navigated around the Moon because at that point in the trajectory, going around was faster and more fuel efficient than trying to reverse course and come straight back, and used the Moon's gravity and a precisely timed engine burn on the far side of the Moon to set them on a return trajectory toward Earth. The calculations for that burn were done, partly, with a handheld slide rule, because the guidance computers had been powered down to conserve electricity. In 1970, a human being with a slide rule was doing orbital mechanics calculations that a modern laptop could complete in milliseconds, and the calculations had to be right because a wrong burn could send the spacecraft skipping off the atmosphere or plunging into it at the wrong angle, and there was no second chance. Then there was the carbon dioxide. The crew was exhaling carbon dioxide into the sealed volume of the lunar module, and the canisters of lithium hydroxide that absorbed it, the scrubbers that kept the carbon dioxide level from rising to toxic concentrations, were being consumed faster than planned because there were 3 people breathing instead of 2. The lunar module's canisters were running out. The command module had plenty of spare canisters, but the command module's canisters were square. The lunar module's receptacles were round. The canisters were literally the wrong shape to fit where they needed to go, and as the carbon dioxide levels in the cabin began to rise toward dangerous concentrations, an engineer at Mission Control in Houston named Ed Smiley led a team that had, perhaps, a few hours to solve the problem before the crew began experiencing the cognitive effects of carbon dioxide poisoning, headaches, confusion, impaired judgment, at which point solving anything becomes considerably harder. The solution they devised used only materials that were confirmed to be on the spacecraft: the cardboard cover from a flight manual, plastic storage bags, duct tape, a tube from a suit pressure relief system, and a sock. They built a prototype in the room in Houston. They took photographs. They called the crew and walked them through building the same device in the spacecraft, step by step, with no room for error and no opportunity to try again if it didn't work. The improvised scrubber, which mission controllers nicknamed the mailbox, worked. The carbon dioxide levels dropped. The crew did not lose cognitive function. And the mission, against odds that no reasonable person would have bet on, continued toward a viable outcome. April 17th, 1970. The crew transferred back into the cold, powerless command module for re-entry. No one was certain the heat shield had been damaged in the explosion. No one was certain the parachutes would deploy after the systems had been powered down and then restarted in near-freezing temperatures. The command module hit the atmosphere at the correct angle. The heat shield held. The parachutes opened. The capsule splashed down in the South Pacific, roughly 6 kilometers from the recovery ship USS Iwo Jima. Jim Lovell, Jack Swigert, and Fred Hayes were alive. It is one of the most extraordinary survival stories in human history, and it deserves every word of the telling. But in the context of everything we have been discussing, the dependence of human life in space on conditions that can fail, on engineering that can fail, on proximity to resources that may or may not be reachable in time, there is a specific detail about Apollo 13 that I want you to hold on to, because it changes the meaning of the story entirely. Apollo 13 survived because Earth was close. The communication delay between the spacecraft and Houston at 200,000 miles was measured in seconds, less than 2 seconds, at the speed of light. That meant that every decision the crew made, they made with mission control fully in the loop, responding in near real time, drawing on the combined knowledge and resources of the entire American space program engineers, flight surgeons, propulsion specialists, chemists, mathematicians, all of them working the problem simultaneously, in real time, with full information. The improvised scrubber was designed on Earth and transmitted to the crew in minutes. The trajectory calculations were checked and rechecked on Earth before the crew executed the burn. Every step of the re-entry procedure was reviewed and confirmed by people on the ground who could see the full picture and respond immediately to new information. Now move that accident. Take the exact same failure, the same ruptured oxygen tank, the same blown hull panel, the same dying fuel cells, and place it not 200,000 miles from Earth, but 50 million miles from Earth, halfway through the 6-month transit to Mars. The communication delay at that distance is not 2 seconds. It is between 3 and 22 minutes each way, depending on where Earth and Mars are in their respective orbits. A question asked by the crew does not get an answer for 40 minutes at minimum. An emergency that requires immediate coordinated response cannot receive coordinated response in real time. Mission control can watch. Mission control can advise with a lag. Mission control cannot act. There is no trajectory option that gets the crew home in days. The minimum energy return trajectory from the Mars transit path takes months. There is no rescue mission, no spacecraft can be assembled and launched in time to make a difference. There is no recovery ship in the South Pacific. There is nothing at all in any direction except the empty space between two planets that are both, from the perspective of the broken spacecraft, enormously far away. Earth's proximity to Apollo 13 was not a detail of the story. it was the whole story. The improvised scrubber worked because the people who designed it could communicate with the people who had to build it in near real time. The trajectory correction worked because teams of mathematicians on Earth could verify the calculations before the burn. The re-entry worked because mission control could monitor every parameter and guide the crew through the procedure step by step. Remove the proximity and you remove all of that. You are left with 3 people in a damaged spacecraft, with a problem they may not be able to solve alone, and a planet that can see them and grieve for them and is completely unable to help. The safety net of Apollo 13 was not the engineering. The engineering had already failed. The safety net was Earth itself, its closeness, its reachability, the fact that the people who knew how to fix the problem were only a light second away. And beyond low Earth orbit, and certainly beyond the Moon, that safety net does not exist. The further you go, the more completely you are on your own. And the universe, as we have been establishing piece by piece throughout this journey, has no interest whatsoever in making that easier. Part 11. The Distance Problem. The Parker Solar Probe, launched in August 2018, is the fastest human-made object ever built. At its closest approach to the Sun, skimming through the outer corona at a distance that would vaporize most materials we know how to work with, it travels at approximately 692,000 kilometers per hour. That number is large enough to be difficult to feel, so let me translate it into something more tangible. At that speed, you could travel from Earth to the Moon in roughly 30 minutes, New York to Los Angeles in about 15 seconds, the entire circumference of Earth in under 4 minutes. It is, by any measure of human engineering achievement, an extraordinary thing. A spacecraft the size of a small car, wrapped in a carbon foam heat shield, diving repeatedly into the atmosphere of a star and coming back to tell us what it found. And at that speed, the fastest we have ever moved anything, the absolute frontier of human propulsion technology as it currently exists. It would take approximately 6,500 years to reach Proxima Centauri, the nearest star to our Sun, 4.2 light-years away, the closest neighbor in what is, by any honest accounting, an incomprehensibly large neighborhood. 6,500 years. I want you to really sit with that number rather than letting it wash past you the way large numbers tend to do. 6,500 years ago, the Egyptian pyramids at Giza were being built. The wheel had been invented perhaps 1,000 years earlier. Writing, as a technology, was just emerging in Mesopotamia. If you had launched the Parker Solar Probe toward Proxima Centauri on the day the first stone was laid at Giza, it would arrive at its current maximum speed in approximately the year 8500. Your descendants, not your children, not your grandchildren, but the people who share some fraction of your DNA roughly 4,000 generations from now, might be picking up the signal. Assuming anyone is still around to listen, assuming the civilization that launched it still exists in any recognizable form, assuming the probe itself has survived 6.5 millennia of interstellar travel through a medium that is not actually empty, that contains dust and gas and the occasional particle moving at energies we still do not fully understand. 4.2 light-years is the nearest star. The Milky Way, the galaxy we live in, is about 100,000 light-years across. The distance to Proxima Centauri, which already seems impossible, is roughly 1/25,000th of the width of our own galaxy. Andromeda, the nearest large galaxy to ours, sits about 2.5 million light-years away. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in every direction. These are the scales on which the universe actually operates. And human beings, with the best technology we have ever built, operating at speeds we have never before achieved, are capable of covering a fraction of 1 light-year across a single human lifetime under the most optimistic conditions currently conceivable. We are, in the most precise and literal sense, local. extraordinarily, almost absurdly local. This is the context in which the concept of generation ships has to be understood, not as science fiction, though it has been that for a long time, but as a genuine engineering and philosophical problem that a small number of serious researchers have begun to examine with real rigor. The premise is straightforward enough. If no single human lifetime is long enough to complete an interstellar journey, then perhaps the journey could be completed across multiple lifetimes. You launch a spacecraft large enough to be a world unto itself, large enough to house not just a crew but a community, with enough genetic diversity to remain biologically viable across centuries of isolation, with agriculture and manufacturing and medicine and education and governance all operating within the hull of a vessel moving through the void. The first generation sets off. Their children grow up aboard the ship, knowing no other home. Their grandchildren are born into a journey that has already been underway longer than any living memory aboard the ship. And eventually, some generation, the 5th, the 10th, the 50th, depending on the destination and the speed, arrives somewhere. The engineering challenges of such a vessel are genuinely interesting and genuinely difficult, and the theoretical frameworks for thinking about them have become more sophisticated in recent decades. You need a closed-loop life support system that can recycle air, water, and nutrients with essentially perfect efficiency, indefinitely, without access to resupply or repair from outside. You need a power source that can sustain the ship, not for years or decades, but for centuries or millennia, something that nuclear fission could theoretically provide. Though the engineering of a reactor designed to run maintenance-free for 1,000 years is not a problem anyone has come close to solving, you need a radiation environment inside the ship that does not kill everyone within a few generations, which means shielding against the same galactic cosmic ray flux we have been discussing throughout this video, now sustained not for months, but for the entire duration of the voyage. You need redundancy in every critical system, because a failure you cannot repair from outside with no resupply possible is a failure that ends the mission permanently. But here is the challenge that no amount of engineering can address, because it is not an engineering problem. It is a human one. And in some ways, it is the most interesting problem of all. The people who board a generation ship and set off into interstellar space are making a decision, a consequential, irreversible decision. But they are not only making it for themselves, they are making it for every person who will ever be born on that ship. Children who had no say in the boarding, grandchildren who will grow up in a metal corridor with no sky, great-grandchildren who will have no concept of what it means to stand on planetary soil and feel wind. These people did not consent to the mission. They cannot consent to the mission because they do not exist at the moment the decision is made. And yet the mission will be the entire context of their lives, the walls of their world, the horizon of every possibility available to them. The ethical questions this generates are not rhetorical. They are genuinely unresolved. In what sense is it acceptable to impose a purpose, reach this star, plant this colony, continue this voyage on people who were born into that purpose without choosing it? What rights do the third generation have to redirect the mission, to turn around, to choose a different destination, to simply stop and live out their lives in whatever part of space the ship currently occupies? What happens when the majority of people aboard, 300 years into a 600-year journey, decide they don't believe in the destination anymore? The founders are dead. The destination is still 300 years away, and the people alive in that moment are not explorers. They are passengers on a voyage they never booked. These are not questions that orbital mechanics or materials science can answer. They are questions for philosophy and ethics and political theory, fields that have historically been given rather less funding than aerospace engineering, and it shows. Then there are the propulsion concepts, the technologies that might, in theory, make interstellar travel fast enough to be completed within a single human lifetime or something approaching it. Fusion drives, which would use the same nuclear reaction that powers the sun to generate thrust. Antimatter engines, which would annihilate matter and antimatter to release energy at the theoretical maximum efficiency allowed by physics. Laser sail systems, in which a spacecraft unfurls a sail the size of a city and is pushed by a beam of focused light from an array of lasers the size of Texas, accelerating to a significant fraction of the speed of light over the course of years. These concepts are all theoretically coherent. The physics, on paper, allows them, and all of them are, at present, either not demonstrable at any scale relevant to interstellar travel, or dependent on engineering capabilities that do not exist and have no credible development timeline. Fusion power is the most instructive example. It has been described as the energy source of the future for approximately 60 years, and the common joke among physicists is that it has been 30 years away for 6 decades running. Controlled fusion has been achieved in laboratory conditions. Net energy gain, where the fusion reaction produces more energy than it consumes, was first demonstrated at the National Ignition Facility in December 2022, a genuine milestone. But the distance between that milestone and a fusion drive capable of accelerating a crewed spacecraft to interstellar speeds is not a matter of incremental engineering. It is a matter of solving problems we do not yet know how to frame. Antimatter production, meanwhile, currently happens in particle accelerators at quantities measured in nanograms, billionths of a gram, at costs of billions of dollars per microgram. An interstellar mission would require it in metric tons. The gap between nanograms and metric tons is not an engineering challenge. It is a category difference. And all of this, every engineering obstacle, every unsolved propulsion problem, every unresolved ethical question about generation ships exists before we return to the problem that has been present throughout this entire discussion, the problem of the body. Because the human body's incompatibility with space does not become easier to manage with distance, it becomes harder. Every additional month of radiation exposure adds to the cumulative dose. Every additional month of microgravity accelerates bone and muscle loss. Every additional month of confinement and isolation in a closed system adds to the psychological load carried by the crew. The further from Earth you are, the more perfectly the artificial environment must function, because the consequences of failure are total and the possibility of rescue is zero. And the further from Earth you are, the less likely that perfect function becomes, because no engineered system operates indefinitely without failure, and there is no one coming to fix it. The central truth of human biology in space reasserts itself regardless of the scale at which you examine it. It is the same truth whether you are looking at 14 seconds in a Houston vacuum chamber or 14,000 years in a vessel crossing the void between stars. The human body is not a generalized machine that can be made to run on any available fuel in any available environment. It is a specific organism shaped by a specific planet, calibrated to a specific gravity and a specific atmospheric pressure and a specific radiation environment and a specific temperature range. It works here. It works remarkably well here. And the further you take it from here, the more clearly you can see that here is what it was always built for. And that world, this world, seen from sufficient distance, is barely a speck, a pale point of light in the dark. The only place, as far as anyone has ever been able to determine, where the conditions exist to make something like us possible, which raises a question that might be the most important one we have asked all night. How did those conditions come to exist in the first place? And what does it mean that they are here at all? Part 12. The thin shell of atmosphere. Step back far enough and the whole picture changes. Not your perspective on it, the actual picture. Because there is an image, a specific way of seeing Earth that most of us have absorbed at some point, without really stopping to process what it means that reframes everything we have been talking about tonight. It is the image of Earth from orbit or from the moon, or from somewhere out in the outer solar system where the planet has shrunk to something you could cover with your thumbnail. And the thing about that image that never quite gets said plainly enough, the thing that tends to get glossed over in favor of comments about how beautiful it looks, is this: the atmosphere is not visible. Not as a sphere, not as a distinct layer, not as a presence you would notice if you didn't already know to look for it. It is the thinnest possible skin on the surface of the planet, a blue-white haze so delicate that it registers less as a feature and more as a suggestion. From low Earth orbit, it clings to the edge of the world like the glow around a lamp in fog, barely distinguishable from the darkness beyond it, easily overlooked, the kind of thing your eye moves past while looking for something more substantial. That haze is everything. That haze is the entire reason this conversation is possible. The atmosphere extends upward for about 100 kilometers before it fades, gradually and then completely, into space, though most of its mass, most of the pressure and oxygen and chemistry that keeps biology running, is concentrated in the first 10 to 15 kilometers. The layer that actually sustains life is thinner than the haze you see from orbit suggests. Thinner, in fact, than the skin of most fruits relative to the fruit itself. Compared to Earth's radius of about 6,371 kilometers, the breathable atmosphere is a layer 100 kilometers thick, wrapped around a ball, 6,300 kilometers across. The ratio is roughly that of the shell of an apple to the apple, or the skin of an onion to the onion. The structure beneath the rock, the mantle, the liquid iron outer core, the solid iron inner core, is enormous, ancient, and essentially irrelevant to the question of whether you can breathe. The skin is the whole story. Everything else is just the thing that holds the skin in place. And inside that skin, packed into that implausibly thin shell of gas that wraps this particular rock at this particular distance from this particular star, is everything we have spent this entire video cataloguing. The pressure of approximately 1 atmosphere, maintained by the weight of the air column above you, that keeps the water in your body in liquid form and the gases in your blood in solution. The oxygen, at a partial pressure of about 21 kilopascals, that your hemoglobin is specifically shaped to bind and carry and release at the precise pressures your tissues require. The ozone, concentrated in a layer between 15 and 30 kilometers altitude, that absorbs the ultraviolet radiation streaming in from the sun before it reaches the surface and breaks the chemical bonds in your DNA. The carbon dioxide and water vapor that trap infrared radiation and keep the surface temperature above the freezing point of water, making liquid oceans possible, making chemistry possible, making the whole experiment of life possible. The nitrogen that makes up 78% of the atmosphere by volume and does essentially nothing biologically, while doing something critically important, physically diluting the oxygen to a concentration where fire is. Possible, but not overwhelming, where combustion is a tool rather than a catastrophe. All of it working together. All of it simultaneously. All of it interdependent in ways that make the system almost impossible to reduce to individual components, because the components did not evolve independently. They evolved together across billions of years, each one shaping the others, the whole system drifting toward a state that turned out to be extraordinarily good at sustaining the kind of chemistry that produces something that can eventually look up and wonder about it. And above that skin, above it, starting not gradually, but essentially immediately, within a few kilometers of the top of the layer we live in, is everything we have described tonight. The vacuum that takes useful consciousness in 14 seconds and life in 90. The radiation that threads through spacecraft walls and accumulates in bone marrow and may, over the months and years of a long mission, begin to quietly alter the architecture of a human brain. The cosmic rays, some of them carrying the kinetic energy of a thrown baseball in a single subatomic particle, that Earth's magnetic field bends away from us every moment of every day, without our awareness or our gratitude. The microgravity that teaches the skeleton it is no longer necessary, that redistributes fluid toward the head until the optic nerve swells and vision blurs, that begins to change gene expression in ways that persist after return. All of it starts at 100 kilometers. The edge of the survivable envelope is not somewhere out there among the planets. It is not at the orbit of the Moon, or the asteroid belt, or the outer solar system. It begins at an altitude that, if you could drive straight up, you would reach in about an hour on a highway. In most inhabited parts of the world, 100 kilometers is less than the distance from one city to the next. It is, by any ordinary human measure of distance, extremely close. The fact that it feels far away is a function of how we move, not how far it actually is. The magnetosphere extends much further, which is fortunate, because what it is protecting us from requires a much larger shield. It stretches out to tens of thousands of kilometers on the sunward side of Earth, and much further on the night side where the solar wind pushes it into a long tail. It is not a visible structure. It is a field, a consequence of the movement of liquid iron in Earth's outer core, generating electrical currents, generating a magnetic field, the same basic physics as an electric motor, but operating at planetary scale across geological time. You cannot see it. You cannot feel it. The only reason most people know it exists at all is because of the auroras, where charged particles from the sun spiral down the magnetic field lines near the poles and collide with atmospheric molecules and produce those curtains of green and red and violet light that people travel thousands of kilometers to photograph. The auroras are beautiful. They are also, if you know what you are looking at, a visualization of the magnetosphere doing its job, catching particles, channeling them safely, showing you where the shield is working. Without the magnetosphere, the shield fails. And the evidence for what happens when a planet's magnetic shield fails is sitting, cold and thin-aired and largely dead, about 78 million kilometers away from us right now, depending on where we are in our respective orbits. Mars once had a magnetic field. We know this because we can detect the remnant magnetism preserved in ancient Martian rocks, stripes of magnetization frozen into the crust, recording the direction of a field that no longer exists, like a compass pointing toward a north pole that disappeared billions of years ago. The Martian dynamo, the churning liquid iron core that generated the field, shut down somewhere between 3.7 and 4 billion years ago. The reasons are still debated. Mars is smaller than Earth, and smaller planets cool faster. And a cooled core stops convecting. And a core that stops convecting stops generating a magnetic field. Whatever the precise cause, the field weakened and then effectively disappeared. And without the field, the solar wind, the constant stream of charged particles flowing outward from the sun at several hundred kilometers per second, began to strip the Martian atmosphere away, particle by particle, molecule by molecule, over geological timescales. The result is what we see today. Mars has an atmosphere that is roughly 1% of Earth's atmospheric pressure, composed almost entirely of carbon dioxide, with traces of nitrogen and argon and almost no oxygen. It is cold enough that carbon dioxide itself freezes out at the poles in winter, forming dry ice caps. It is thin enough that it provides almost no protection against ultraviolet radiation. The surface of Mars receives a UV dose that would be lethal to most unprotected life on Earth's surface. It is thin enough that it burns up almost nothing small meteoroids that would be harmlessly incinerated in Earth's thicker atmosphere reach the Martian surface intact. It is far too thin to maintain liquid water for more than moments under most conditions, because the atmospheric pressure is below the triple point of water, the pressure below which water cannot exist as a liquid at all, only as ice or vapor. Water on Mars sublimates directly from ice to gas. Liquid water, if it forms at all, evaporates almost immediately. Mars may once have been different. The geology suggests it. Ancient riverbeds, carved channels, valley networks that required sustained liquid water flow over long periods, all of it points to a Mars that billions of years ago had a thicker atmosphere, a warmer climate, and possibly liquid water on the surface. A Mars that was, in some ways, more like Earth. And it lost all of that. Not because of a catastrophe, not because of an impact or an explosion, but because the internal engine that powered the magnetic shield ran down. And without the shield, the atmosphere went. And without the atmosphere, the water went. And without the water, whatever was there, whatever chemistry was running in those ancient rivers and lakes stopped. Earth has kept its shield because the dynamo in its core is still running, partly because Earth is larger than Mars and has cooled more slowly, partly because the presence of the Moon, which stabilizes Earth's axial tilt and may have contributed to maintaining the convection currents in the mantle, has helped keep the interior dynamic. The Moon, which most people think of as a convenient source of tides and a nice thing to look at on clear nights, is part of the life support system of this planet. Its gravitational influence on Earth's rotation and interior is one of the threads in the web that keeps the conditions for life in place. Pull any of the threads and the web changes. Pull enough of them and it fails. The ozone layer tells a similar story of contingency and interdependence. It was not always there. For the first 2 billion years or so of life on Earth, there was essentially no ozone layer, because there was essentially no free oxygen in the atmosphere. The early Earth's atmosphere was rich in methane and carbon dioxide and nitrogen, with almost no molecular oxygen. Life existed, but it was microbial, and it lived in the ocean, which provided shielding from ultraviolet radiation. Then, somewhere around 2.4 billion years ago, a group of bacteria, cyanobacteria, the ancestors of the chloroplasts in every plant alive today, evolved the ability to perform oxygenic photosynthesis. They began to split water molecules using sunlight, releasing oxygen as a waste product. And over hundreds of millions of years, that oxygen accumulated in the atmosphere. It reacted with existing methane and other reduced gases. It built up, and eventually, in the stratosphere, ultraviolet radiation split oxygen molecules and reformed them into ozone, and the ozone layer began to accumulate, and ultraviolet radiation levels at the surface dropped dramatically, and complex multicellular life began to colonize the land. You are standing in the result of 2 billion years of microbial waste disposal. The ozone layer that protects your DNA from ultraviolet damage is made of the exhaled byproduct of ancient bacteria. The invisible shield 20 kilometers above your head is biological in origin. It was made by life, for life, over a span of time so long that if you compressed the entire history of Earth into a single calendar year, the ozone layer would not become significant until sometime in late summer. The temperature regulation of Earth's atmosphere deserves the same patient attention, though I am aware that the phrase greenhouse effect now arrives with a certain amount of political freight attached. The physics, to be clear, is not political. It is simply the mechanism by which certain gases, carbon dioxide, water vapor, methane, nitrous oxide, absorb infrared radiation emitted by the warmed surface and re-emit it in all directions, including back toward the surface, rather than allowing it all to escape directly to space. Without any greenhouse effect at all, Earth's average surface temperature would be approximately minus 18 degrees Celsius. The entire surface would be frozen. The oceans would be ice. The chemistry of life, which requires liquid water as a solvent, would be impossible. With the natural greenhouse effect operating at its pre-industrial, pre-human baseline, the average surface temperature is approximately plus 15 degrees Celsius. The difference, 33 degrees of warming, is entirely the contribution of a trace of gas in a thin atmosphere on a small planet. 33 degrees between a frozen rock and a living world. That warming has been maintained within limits that allowed liquid water to persist for roughly 3.5 billion years, through ice ages that covered much of the planet in glaciers, through warm periods when there were no polar ice caps at all, through the mass extinctions that periodically reset the biological experiment. Through all of it, The temperature never swung far enough in either direction to boil the oceans or freeze them permanently. The carbon cycle, the movement of carbon through living things and the ocean and the rock over millions of years, has functioned as a long-term thermostat, pulling carbon dioxide out of the atmosphere when temperatures rise and releasing it when they fall, buffering the system against extremes that would otherwise be inevitable. It is not a perfect thermostat. It is a slow, geological thermostat with a response time of hundreds of thousands of years. But over 3.5 billion years, it has kept the range survivable. That is, by any measure, an extraordinary run of luck, or physics, or both. When you look at the universe as a whole, not at the pictures of nebulae and galaxies that appear in astronomy books, which are beautiful but unrepresentative, because they show the luminous fraction of a universe that is mostly dark and cold and empty, the conditions that exist on Earth's surface begin to look profoundly unusual. The interstellar medium, the material that fills the space between stellar systems, is vacuum by any practical definition. The density is perhaps 1 atom per cubic centimetre on average. The temperature, depending on where you are, ranges from a few degrees above absolute zero in the cold molecular clouds where stars form, to tens of thousands of degrees in the warm ionized gas between the clouds, to millions of degrees in the plasma of stellar coronae and the remnants of supernova explosions. There is radiation. There is no pressure to speak of." End quote. There is no chemistry of the kind that requires liquid water and moderate temperatures and the right mix of elements in the right concentrations. The fraction of the universe's volume that simultaneously meets all of the conditions required to support human life, without any engineering assistance whatsoever, is so small as to be essentially unmeasurable. It may, for all we currently know, be unique. It may be this one planet and nowhere else. This is the quiet context in which Enrico Fermi asked his famous question at a lunch table in Los Alamos in 1950. If intelligent life is common in the universe, where is everybody? It is a question that sounds simple and opens into something genuinely unresolved. The universe is 14 billion years old. The Milky Way contains somewhere between 100 and 400 billion stars. A significant fraction of those stars have planets. Some fraction of those planets are in the habitable zone where liquid water is possible. Given the age of the universe and the number of opportunities, even a very low probability of intelligence arising should produce a galaxy full of civilizations, some of them billions of years older than ours, some of them presumably capable of making their presence known across interstellar distances. And yet we detect nothing. No signals, no structures, no evidence of anyone. The proposed resolutions are many, and none are settled. Perhaps life is rare. Perhaps the step from chemistry to biology, from molecules to self-replicating systems, is so improbable that it has happened only once or a handful of times in the observable universe. Perhaps the step from simple life to complex multicellular life is the rare one. Perhaps intelligence arises commonly, but civilizations destroy themselves through war or environmental catastrophe, or the development of technologies that outpace their wisdom before they become detectable. Perhaps the distances are simply too large and the signals too faint, and we have not been listening long enough or broadly enough to hear anything, even if there is something to hear. We do not know. We genuinely, honestly, at the frontier of our best science, do not know. What we do know is that the conditions required to produce a technological civilization are each, individually, contingent. A planet in the right orbit, a star of the right type and age, a magnetic field to protect the atmosphere, a large moon to stabilize the axial tilt and slow the rotation to livable day lengths, the right proportion of heavy elements, carbon, nitrogen, oxygen, phosphorus, the atoms of biology delivered by ancient supernovae that preceded the formation of the solar system, an atmosphere that evolves in the direction of oxygen rather than in any of the other directions it could go. No large-scale catastrophe, asteroid impact, nearby gamma-ray burst, runaway greenhouse, arriving at the wrong moment and ending the experiment before it produces anything interesting. Each of these conditions has to be met, and the probability of all of them occurring together, in the right sequence and the right timing, is a number that honest researchers disagree about by many orders of magnitude. The optimists think it happens fairly often. The pessimists think it may have happened exactly once. Let me bring us back to where we started tonight, because that is where the answer has been waiting all along. Jim LeBlanc, December 1966. Houston, Texas. A man watching his own saliva bubble on his tongue, in a room designed to show us what exists on the other side of the thin shell above us. 14 seconds of useful consciousness. Survived because someone was at the controls, because the chamber could be repressurized, because Earth was right there. Georgy Dobrovolsky. Vladislav Volkov. Viktor Patsayev. June 29th, 1971. 168 kilometers up. 2 minutes. A valve the size of a coin. No one at the controls who could help. They came home in their seats, peacefully, hours after the physics had finished with them. These stories are not history. They are demonstrations. The universe demonstrating, on human bodies, with perfect dispassion, what the rules actually are. The engineering failed. The physics did not. The physics never fails. It just runs its equations on whatever material is available. And if that material happens to be 3 cosmonauts inside a re-entry capsule, the equations run the same as they would on anything else. The human body requires pressure, oxygen, radiation shielding, gravity, temperature stability, all of it, simultaneously, without interruption, for decades. On Earth, the planet provides all of this, automatically, continuously, without a single moving part that requires maintenance. As the accumulated output of 4 billion years of geological and biological history that was not planned, not engineered, not optimized, it just happened, one contingent step at a time, and it ended up here. Space is not the dangerous thing. Space is what the universe normally looks like. Space is the default. The vacuum and the radiation and the cold and the silence that is just what you get when nothing unusual is happening. Earth is the unusual thing. Earth, with its spinning iron core and its thin blue atmosphere and its liquid water and its ozone and its moon and its carbon cycle and its 3.5 billion years of unbroken biological continuity. Earth is the anomaly. Earth is the thing that requires an explanation, and we do not yet fully have one. We cannot survive space because we are not built for space. We are built for this specific pressure, this specific oxygen concentration, this specific gravity, this specific radiation environment, this specific temperature range. We are built for one planet, and it is the one we are on. The further we go from it, the more completely we understand that every detail of what it provides was load-bearing, that none of it was decoration, that the thin shell of atmosphere above your head is not a backdrop, it is the machine, and you are what the machine makes possible. The 14 seconds Jim LeBlanc had in that chamber were not a warning, they were a measurement of exactly how far the machine extends, and exactly where it stops, and exactly what we are on the other side of it, which is to say, exactly what we are without it, which is to say, not much and not for long, and somewhere in one of the 2 trillion galaxies visible to our telescopes, across a distance so large that the number has no intuitive meaning, there may be another machine, another thin shell, another spinning rock with an iron heart and a carbon cycle and a moon in the right place and a star at the right distance, another improbable, contingent, unrepeatable accident of physics that produced something warm enough and stable enough and long-lasting enough for chemistry to become biology and biology to become thought and thought to look outward and ask the same question we are asking tonight. And if that question is being asked, it is being asked from inside a thin shell of atmosphere, because that is the only place, as far as we have ever been able to determine, from which it is possible to ask anything at all.